So another important property of the Brownian motion and other processes more generally, this is very useful for, used widely in math finance to, pricing options and other financial contracts. And so, I think you find it in Ross in section 10.4. I think towards the end there's a remark, but let me give you a kind of a cleaner definition here. So this, so Martingale, if X has the Martingale property, we're just going to call it a Martingale. That means the same thing. So here I have a continuous time process X, and it's said to be a Martingale or to have the Martingale property if two conditions hold. One is if it's quote unquote integrable. That just means that the expected value of its absolute value at time t is finite, or in other words, the absolute value has a finite expectation at any time t. And this property is perhaps a little bit more interesting. So we're kind of thinking of two time points, time s and time t, and s is going to be the present, and everything before time s is the past, and t is in the future. And so you're kind of sitting, having observed the path of this process x. We're sitting there at time s, and we've seen the entire kind of history of it in the past, and we're asking what is the best prediction of this process at time t in the future. And the answer, if you want x to be a Martingale, better be the current location, wherever our best prediction of the future is the current value. So perhaps this is even a little bit easier to say when x is Markov, or if x has the Markov property. Here we're just saying that our best prediction of a future value of x at a future time t is the current value, meaning xs itself. And this is all kind of related to the theory of games and gambling, and kind of the idea being that if I have some stock perhaps, and sort of maybe say I'm going to buy this at time s and then sell at time t, hoping to make a profit, right? So the idea, if you want to make a profit like this, you want to buy low and sell high. And kind of here's the picture with the Brownian motion being the example. So at time s I'm going to buy the stock at this price, whatever that is. Maybe it's like 5 or something, and I'm going to wait, and here it looks like I'm kind of screwed a little bit, and then here it comes up, and at time t it's already up here. So I've made this much profit. So this increment in fact is the amount of profit that I make. And the Martingale property, basically, it doesn't say that you can't ever make a profit, but it says that on average, in expectation, you shouldn't make a profit, meaning that whatever I bought the stock for, I should expect it to have the same exact price in the future. And so the fair game part refers to whether you're buying or selling. It kind of doesn't matter. Neither side on average is going to win. So we can kind of run some of these calculations, not calculations, but how do you verify this Martingale property for an example we're familiar with now. So we'll take the Brownian motion starting at x with the volatility sigma, and we ask is it a Martingale. So first thing you want to do is not that this is usually forgotten, but kind of the forgotten part of the definition, but it is important. And so we can try to compute the expected the expectation of the absolute value of w at t. And I guess there's sort of an easy way and a hard way, and I did it kind of maybe the hard way here, but this is still worthwhile to go through, and then I'll show you the easy way, which is on the board behind me. So first of all, hopefully you all know what the density is of the probability density function of the Brownian motion time t. It's just normal with mean x, and variance sigma squared t, and this is actually going to be also related to our transition probability. So this is in fact a this is also a transition probability that we had in the previous clip. In t time units, we better go from x, in here, I guess it's that to y. So this pt xy, the transition probability of the Brownian motion from x to y, is exactly this psi x ty, the same normal density. And what am I taking the expectation of? It's the absolute value, and so I'm integrating over all possible places where the Brownian motion could be, and that's the variable y there. And so you look at this and you can kind of start looking up integral tables and so on and so forth, and we're not really even concerned with how to compute this expectation. If you want to look this up on, I think on probably Wikipedia, you can find what's called the folded normal distribution. It's folded because you've taken the absolute value, kind of folding. So this is a normal distribution, and it has maybe negative values over here. The idea of a folded one, you take the absolute value and you fold this piece, the whatever probability mass is on this side. I didn't draw it out, but it's obviously it keeps going. So all those negative values would get folded onto the other side. So if you want to see kind of how to compute explicitly the mean of that folded normal, which is the expected value of the absolute value of w at time t, you can see that Wikipedia page. But here we don't really need that. We just need to bound it above. We just need to make sure that it's less than infinity. And so one trick you could do is add and subtract an x, and the reason I'm doing this is because I need this term to make the integral look a little bit easier. I have y minus x here, and so I'm trying to mirror that on this side in the next step here. And then here there's an application of the triangle inequality. I'm trying to bound above, and this is a triangle inequality that I'm applying here. This is a I guess absolute value is sort of the Euclidean length on the real numbers, and so hopefully you're familiar with this type of bound. And that leads me here. The x that popped out on this side got integrated out. The thing next to it was the probability density function integrated from minus infinity to minus infinity, so that was just 1. So the term, this term next to the absolute value of x just integrated out to 1 by the definition of probability density. And this one stays, but it's much easier to work with. The idea here is that I'm kind of, I guess you can go to this step here where I've written that this integral is just the integral from x to infinity of the same exact integral times 2. So why do I say that? So kind of the idea is in this picture really, if I'm integrating y minus x, then the idea is that this is just the integral centered at x, and so basically what this is being asked for is the area under the curve going down this way plus the area under the curve going up that way. And what I'm saying is it's much easier for me to go from in this case from x to infinity, which means I'm going to integrate just half of this distribution. So I'm going to compute the area under the curve going up from here, and then I'm going to multiply it by 2, because I would have obtained the same answer by integrating the area under the curve going down this way. And that's where this 2 comes from. So you can even look up, I don't remember where I found this, but you can look up exactly what this integral evaluates to and check my answer. But this is the final thing that I got, and of course the absolute value of x is still kind of with us, but the point is that this is less than infinity. This is all we were really after. And so the first part of the Martingale property has been verified. I want to mention that there's a much easier way of doing this. So this is an important result to know. This is called Jenkins Inequality. So the idea is that if you have any random variable, here it's x above, and phi is some convex function, the idea is that you can bring that convex function into the expectation as being done right there and increase the expected value. So here's my attempt to do that here. I have a convex function which is x squared. This is the convex function that I'm using. So up above, phi of x is equal to x squared, and you can see that phi is now applied to the entire expectation, and my random variable x is the absolute value of w at t, and now that's going to be less than or equal to bringing in the function phi into the expectation. So it now over there you see it's expected value of phi of x, and now I have expected value of the Brownian motion squared. And this is just, what's the distribution of the Brownian motion at time t? Here, it's normal, and its variance is sigma squared t. So that's what I put here. And this is really what we wouldn't have gotten, I guess. Well, there's really doesn't need to be any connection between the two, but the point is that this is finite also, and so this was a much faster way of showing what we wanted. If when something squared, from here you clearly see that this absolute value, the expected value of that absolute value is finite. Just take the square root of this side and the square root of that side, and you get a nice bound that's finite. The more interesting property is this one. We already know that the Brownian motion is Markov, so we might as well go with this right away. So here are the steps. I guess I didn't even. I guess here I basically applied the Markov property, so I kind of did one extra step. So W, the Brownian motion, has the Markov property. So starting with, I guess, the original definition up here, I move to this one. So this applies the Markov property of W. Then kind of the common trick is to add and subtract what you want. So I know that I want to get this at the end. So why not subtract it and add it? My conditioning here is the same as it was before. If I know W at time s, which is what I'm conditioning on here, if I know W at time s, then certainly I know W at time s minus W at time 0. This has, this is just the constant value x. That's where I've started. And so you can go, both any which way. If I'm given W at time s, then I know the value of this increment, and conversely, if I know the value of this increment, I can just add x to it to recover my Brownian motion at time s, that value. And so why do this? Well, again, we're going to be using the independence of increments property of the Brownian motion. This increment is independent of this increment, and you just get the Brownian motion at time s plus the expected value of the increment. So this conditioning here goes away, because if you condition on something that's independent of the thing you're taking the expectation of, it just you're allowed to drop it. It's irrelevant as far as the calculation of the expectation. The conditioning here gives me no extra knowledge as to the value of this increment by using this one. So in other words, they're independent. And so I've dropped that conditioning from this expectation. And what do we know about the expected value of the increment? Well, it's normal with mean 0, and therefore it is equal to the expected value is 0. And I pick up the Brownian motion at time s, and now just I directly verified the Markov property. I guess starting from this one, right? Starting from here, I got all the way to here, and we verified the second part. So the Brownian motion is a martingale. That's the short of it. And you can kind of see how this plays out, right? I bought the stock at time s, and it had this value. how much do I gain? What's my profit? Well, it's exactly this difference. I'm going to sell at time t, so the amount of profit I make is w at time t minus w at time s. This is the increment. I'm adding it to the original value, and this is a mean zero normal random variable. So you can see that this being the representative of the amount of profit that I've made, on average it's zero, and so I just recover my my original time s, and obviously this ws cancels out with this ws, so this whole expression is actually equal to wt, the thing that I'm working to make a prediction of, I guess, right here. So let's do this with a few other examples in the next clip.